Okay, so the last thing I want to take a look at in 4.1 we didn't get to was called a mixture problem. So this is going to use the calculator. The biggest thing is we just have to know how to plug in what we're looking for. So let's say that I had a solution of 50 ounces. Had a solution of 50 ounces. And out of those 50 ounces, 35% of what's in that 50 was some type of acid, and to say like the rest of it was just water. How would you figure out if you have 50 ounces and I tell you that only 35% of it is acid, how much out of the 50 is acid? What do you do? 35% of this is what I want to know. Yeah?
I would say you would just multiply it by 2 and then divide by, I would be like, well, it's just, you have 50 ounces. So
or you had a question, let's say you had a test that was 50 questions and you got a 35% on the test. How many questions did you get right? Same thing.
Yeah, so I would just multiply 50 by 2 and then 35 by 2 and then an extra percentage.
Okay. So you could try to convert it out of like 100 just to make it easier.
Yeah, so it would be 70%.
How could you do it
Or sorry,
directly with these numbers? Yeah?
Can't you divide 35 by 2?
Divide 35 by 2?
Yeah.
Yeah, that's basically what it's going to come out to. So you take your number and you multiply by the percentage, which in this case, yeah, it is 35 divided by 2, which is 17.5. So if you had 50 ounces of liquid and I said that 35% of it has acid and the rest of it was water, then that means 17.5 ounces out of the 50 ounces are acid. So is there any question on how I found 35% of 50? That's how I did it right there. Okay, so what we're going to look at in this problem, it's going to be a mixture problem, and it's going to involve a concentration. If you don't know how to figure out the concentration of a solution, I need to show you that. So to figure out, guys, what's up?
What?
What's up? What's that?
Yeah.
Okay. So to figure out concentration of an acid or any solution, it's a fraction. Whenever you're finding a percentage, like whether it's on a test or percentage of anything, what do you usually put in the bottom? It's usually like the, yeah?
Like the percent you're trying to find. So like if you're trying to find 25% of 100, then you just put it like the.
Well, I don't know, this is going to be my percent on this side. But when you're trying to find a percentage and you have like a liquid, let's say I said to you, I have a liquid and 10 ounces out of the 40 ounces have acid. What's the percent acid? What number usually goes in the bottom? Yeah?
Like the whole?
The whole, right? Whenever you're finding a percentage, the total or the whole amount goes in the bottom. And then in the top, you put the amount that you're interested in. The amount, in this case, it would be the amount of acid. So if I had a 10-gallon solution and 3 gallons out of the 10 were acid, if I take 3 divided by 10, that'll tell me the percentage of acid in the solution. So that's the equation that you need. So amount of acid divided by the total. Okay, so let's look at this problem. So we have a solution, and we're going to pour in X ounces of pure acid. Okay, that means that it's not diluted. What we're pouring in is 100% solution. We're going to add that to a mixture we already have. This is the mixture we already have. We have 50 ounces, and out of the 50 right now, it has 35% acid in the solution. I'm going to pour in pure acid to make the solution stronger. So any question on just kind of the setup of what we're doing? So we're going to make the solution stronger. First, I want to find a formula that represents the concentration as you continue to pour in 100% pure acid. So bless you, what's the formula again for concentration?
It's whatever the percentage you're trying to find is the numerator, and then the whole is the denominator.
So the total, yeah, the whole or the total goes in the bottom, and the part in the top is going to be the amount of acid. Okay. So we have to keep in mind, we're starting with a solution and we're pouring acid into it. This is the solution we're starting with. 50 ounces of a 35% solution. So how would I figure out how much acid do we already have in the solution before we pour anything in? Yeah.
Whatever 35% of 50 ounces, which we already decided was 17.5.
Yeah, we already did that. It was 17.5, right? So that's how much acid is already in the liquid to start, 17.5. How much acid are we pouring into it?
100%.
Well, that's the strength of it, but how much of that are we pouring in? X. So when we're done, the amount of acid is going to be how much we already had plus how much we pour in. Now let's figure out how much total liquid will be in the container. How much liquid are we starting with in the container?
50 ounces.
50 ounces. And how much liquid are we adding?
X.
We're adding X. So that is a formula for the concentration. Okay, that's what we're going to graph. Now, before we graph, think a little bit about the concentration. You're starting with a solution that's only 35% acid. If you continue to pour in pure acid, will it ever reach 100%?
No.
No. Because you had some in the solution that wasn't. It's like if you had a can of white paint and you put a drop of black in it. If you keep pouring white into it, you can't get the black out. You can make it less and less and less, but it's still in there and it's part of it now. Does that make sense? Okay. So let's graph that and see what it looks like. So we've got 17, and you want parentheses around this. So we got 17.5 plus X, and we're going to divide that by 50 plus X. Okay, think about our window a little bit. Can you add a negative amount of acid?
No.
No. So we don't want to look at adding negative amounts. As far as the maximum amount of acid, there is no maximum. We just assume we can keep adding as much as we need to. Okay, they didn't say there was a limit. So let's go up to 200 ounces. Now, the concentration. The concentration is always going to be a number between what and what as a percent. Can't go lower than this or higher than this.
0% and 100%.
0% and 100%. What would that be as a decimal? 0 to 100%.
Or 0 and then 1.1.
0 up to
Oh, sorry, 0 to 1.
0 to 1.
I said 1.
Concentration is always measured as a decimal from 0 to 1. Can't go higher than 1. It's not possible.
Wait, why is your y min 0 again? Just because you can't.
You can't have less than 0%. Yeah. The concentration can't go below 0 and it can't go above 1. So that's a graph of the concentration. As you continue to pour in more acid, the concentration gets higher and higher. But it's going to level off at what number and never reach it. 1. You can't go higher than 1, and it'll never reach 1 because you started with a solution that wasn't pure acid. So even if you keep putting hundreds and hundreds of gallons of acid in it, it still has a little bit that wasn't pure acid to begin with.
Can
Okay.
I say what you plugged in for y?
0 to 1.
No, like the y equals.
Oh, the y equals, just like that.
It's just the same.
Well, that's what I did, but I didn't get that on my.
Did you do parentheses?
Yep. And I got a straight line and not no curve.
And you set your window x is 0 to 200?
Yeah, you didn't put your thing to 200.
So make sure, yeah, you just set your window 0 to 200 and set your
Okay.
y min max, and then you should be good.
I got it.
Okay, so that's part A. Find a graph of the concentration. There's the graph as you continue to pour in acid. It gets stronger and stronger. But as you start to pour it in, it starts to level off at some point. Okay? It doesn't make as much of a difference as it did in the beginning. Okay? So now part B says, when will the concentration reach exactly 75%? So I want to know, how much do I have to pour in to raise the concentration to 75%? How would I mark, well, what's 75% as a decimal?
0.75.
0.75. So on y equals, add in a mark or add in a line at 0.75. That line in red shows me where the mixture hits 75%. So what do you think I need to calculate here?
The intercept?
I have to find the intersect. So we're going to do second, calc, intersect. And I get an answer of 80. So that means in order to get this mixture up to 75%, I would need to add in how much acid? 80 what?
Ounces.
Ounces, yeah, because everything in this problem was measured in ounces. Yep. So how much acid do we have to add? 80 ounces. That's it. So that's how you do a concentration problem. When you set it up, it always has a setup like this, where this number is the total liquid you started with. This number was the total amount of acid in that liquid, and then usually you have a variable like that that's x. That's it. Any question on that?
Can we like do another one of those problems?
Okay, so let's say you wanted to get the concentration to 50%. What would you change that decimal to? Yep, you change it to 0.5. And to get it to 50%, do you think you would need more than 80 ounces or less? Yeah, it's already at 35. You're not going to have to add as much. So now do second, calc, intersect. And to get the concentration to 50 ounces, you need to add 50%. You have to add 15 ounces. So you don't have to add nearly as much in that case.
Okay, where'd you get the number 15 from?
The 15 came up when I did the intersect. Second, calc, and then I think it's option 5.
Okay.
There's
And
an
then-
intersection one.
You do what?
There's an intersection one. 5. Second, calc 5.
And then you just press enter on either side, or?
No, it doesn't matter where you press them on each line, as long as you mark each line. And then-
Yeah, with intersect, you don't have to do a left and a right. That's with zeros.
So what'd you put for like answer A and answer B? Doesn't matter. No, on the actual question.
Well, that's the answer to B, 80 ounces.
Understood.
And for part A, it said, find a graph of the concentration. I put my graph down here because I didn't have enough space.
But it was 80 because it was,
80, because that's what the intersection was when we did 75%.
oh, okay, but for when you just put that 50% in, the answer was.
Yeah, you asked me for a different one, so
So
I
the
just
answer
did.
would have been 15 for that one?
That one would have been 15.
Okay.
Yep.
Alright.
All right, so part of what we look at tonight, that'll be on 222. It'll be the 48 A and B. So the last thing we're going to look at is taking one of these graphs that's a rational function and sketching it. There's different cases we're going to look at. Today we'll look at some of them, and then next time we'll look at the rest when you come next academic week. So when we draw rational functions, there are certain things that can happen that would cause us to have to like lift our pencil up and put it back down when we do the sketch. If you have to lift up and put your pencil back down, like in this one, let me do zoom 6. Well, first of all, could you draw each part of that graph without lifting your pencil up and putting it back down? No. It's in two separate pieces. If you have to draw a graph and it's in two separate pieces, that means your graph has like a disconnection in it. It's not connected. So we call that a discontinuity.
What was it that you do to like clear your calculator, like reset like all the windows and stuff?
Just to reset the window, zoom 6. That'll just reset the window. Now, in this one, can you easily tell that those two pieces are not connected?
Yes.
Yeah, definitely. But if I set up a problem where the numerator and the denominator have a common factor, it might not be easy to tell that there's a hole in the graph. Let me type in something a little different. Let me type in x squared plus 5x plus 6. And I'm going to divide by x plus 2. Now, is there a number you're not allowed to plug in for x there? Right, you can't plug in -2. So that's going to separate your graph into two pieces because there's a number you're not allowed to use. Let's hit graph and see if that's obvious. Okay, so what do you think? Does it look like that graph is in two separate pieces? No, doesn't look it. But what number did you say we can't use? Can't use 2. Watch what happens if I try to plug in 2. No, it wasn't 2. Must have been something else. -2. If I try to plug in -2, what does it say?
Error.
It says error. So let me go back to that graph. The calculator can't do this, but what it should look like is this. At -2, there's a hole in the graph. So this is one part. Then there's a hole, so I have to lift my pencil up, put it back down, and then I can start tracing again. The problem with having a hole in the graph is you can't notice it on the screen. The only way that you can see that you have a hole in the graph is if you look at the original problem and factor it. So let's look at, I think I typed in x squared plus 5x plus 6. What did I have in the bottom? X plus 2? Okay. Look at the top. X squared plus 5x plus 6. That's going to factor into two sets of parentheses. How does that factor? X squared plus 5x plus 6.
X
Mm-hmm.
plus 3.
Yep.
X plus 2.
Perfect. And what do you notice about the top and the bottom now?
That they can
Right, they have a common factor. That's the reason why when you graph that picture, you can't see that it's in two separate pieces, because these had common factors. Okay, now, let's say I change the top, instead of being x squared plus 5x plus 6, let's make it x squared plus 5x plus 6.1. Just change the 6 to 6.1. Does the top still factor as x plus 3, x plus 2? No. So now, there will not be an x plus 2 in the top.
It won't say error.
It's going to be very obvious that they're disconnected now. Okay. Does everyone see how it looks a lot more obvious now? That's because I messed up the common factors.
So what does this have to do with anything? Like, is this part of the problem or like what?
Yeah, this is going to be part of the problem. Yep. So let's graph this one. And I want you to tell me, is there a value here that you are not allowed to plug in for x?
Yeah, one's one.
1. All right, so let's try typing this in. Is this going to be a problem where it looks obvious that they're disconnected? Or is it going to be kind of hidden?
I'm just gonna say error probably.
Well, yes, it will say error at 1, whether it's obvious or hidden. Both cases, it'll say the error. But do you think it's going to be easy to see that it's disconnected, or it's going to be hard to see? Yeah, it's going to be hard to see because the bottom and the top have common factors. So when you graph that, it looks like a horizontal line, but it's not. What number are you not allowed to use?
Not allowed to use one.
Not allowed to use 1. So really, there's a hole in the graph right there. That's what I just want you to understand. That sometimes when you draw something on the calculator, it's not always showing it to you accurately the way it should.
And how did you check that again? You did, was it calc or?
Yeah, so if I press second and I go to table, and I type in the number 1, which you can't use, it says error.
It says it already on mine.
Yeah, I might say it already.
Wait, how, is for me it just says. I didn't notice it. It just says, I don't even know what this means,
I'll take a look at it after. Is that one of mine or yours?
It's mine.
Okay, so yeah, it could be set to do all kinds of stuff.
but.
Different. Yeah, you can't plug in 1. Okay, let's take a look at this one. So when you have a hole in a graph, that's a part of the graph that is disconnected. Okay? A hole, that's not really the real name. It's called a discontinuity that's removable. So when you have something that's kind of hidden, and you know it's there, but it's hidden, that's called a removable discontinuity. So something like this, that's a removable discontinuity, because it's a small, very, very small section that you can't see on the calculator that makes the graph disconnected. So think of the word removable as like the word hidden. It's a hidden discontinuity. Compared to something like this. Is that graph in one piece?
No.
No. Is it hidden? That it's not. No, it's not hidden at all. It's very clear. You went like that, and then you lifted your pencil, and you continued like that. That is not a removable discontinuity. To be removable, it has to be hidden. It's hard for you to see it when you draw it. Okay. So any question on what a removable discontinuity means?
This right here?
Oh, sure. Yeah, thank you. Yeah, you get your name on it?
Yeah.
Perfect. Okay, so any question on that, sir? Removable? Just means hidden. Okay, so let's take a look at how we can start sketching rational functions. To sketch something rational, let's start out with something even simpler. Instead of having a rational function, let's just do the top of a rational function. Okay, just the numerator. 3x cubed plus 8x minus 4.
Is it, what's the definition of a rational function? Isn't it like?
A polynomial in the top of a fraction and in the bottom. So let's just start out with something in the top. Let's graph that. So plus y equals, I'm going to do 3x to the third plus 8x minus 4. And I'm going to start with zoom 6. All right, so it's definitely curving, but I can't really see a good picture. So what do I have to do to see this a little better?
You have to zoom in more?
I have to zoom
out.
Yeah, I'm going to zoom out. All right, so let's try setting the y min to like negative 100 and 100. Let's see if that looks any better. Okay, that looks better. Any question on that sketch? Now, I'm going to sketch something else below it. I'm going to sketch just that one. That's the highest term in that top. If you plug in a number for x, like let's plug in 10. What's 10 to the third power?
1,000.
And what's 1,000 times 3?
3,000.
So if you plug in 10, you get 3,000 for that term. What if you plug in 10 here? What's 8 times 10? That's 80 minus 4. 3,000 is way bigger than 80. These two terms start to become less and less important as x gets bigger and bigger. Like if x was 1,000,000 and you cube 1,000,000 and then triple it, that number is just going to be so big it's going to completely overpower the other two numbers. So graphing this first one should give us a pretty good idea of what this is going to look like. So let's graph 3x raised to the third. Just that. What do you think? Does the one in red, that's a lot simpler, look similar to the one that's in blue? Yeah. And if you zoom out, it would look even more similar. So if I do zoom 3 and hit enter and step back even further, there's the blue one. And here's the red one. Look at them now. How similar do they look now that I zoomed out? They look even more similar. So the most important term when you're looking at a polynomial and trying to see what it's going to look like is the one with the highest exponent. These other two terms don't really do that much to it. Okay? They cause maybe little twists and turns, so yeah, it makes it a little bit different in there. But if you zoom out, it looks almost identical. So any question why this first term really controls everything that's going on? The other two terms don't make much of a difference.
Could you go back to your y equals?
The y equals?
Yeah, I think I might have put it in wrong. I don't know. I'm getting like a different picture. How did you do x to the third? Because I just did like the.
You press X, and then the button below clear, and then the 3.
Yeah, I did that. It's just like it doesn't shoot.
Oh, yours is a different calculator, so no, it's going to show it as like a caret, right?
Yeah.
Yeah.
And then, but when I put graph, then it doesn't look like yours. Like yours is sloped different.
And you set, I had to set some pretty big, negative 40 to 40 and 400 to 400.
Alright, that's
Yeah.
not what I did now.
And if you want to use one of mine so it looks
I think it'll look good.
like it, you could also do that too. Okay, so what I'm trying to show you guys here is this first term is what's most important. Right. This term right here is called an EBM. Okay, that stands for End Behavior Model. And what that basically means is if you graph the whole thing and then you graph just the term with the highest exponent, and you zoom out enough, the EBM will look exactly like the original graph. Or it'll look pretty close. If you zoom in, no, it won't. But if you zoom out, right, pretend like you're looking at it from outer space, they're basically going to look the same. And the reason why we like an EBM is because it's simple. It doesn't have all this extra stuff in it. So the EBM is a simple way to describe generally what the graph is going to look like. Generally. But it's pretty close, as you can see from that. It's very close. So now what we want to look at is, let's make one up for you. Let's say we had, don't worry about anything above the blue line. So 8x cubed minus 4x squared plus 6x minus 5. And we want to divide that by x to the 4th minus 2x plus 6. And I want to get an idea of what this is going to look like. There's a lot of terms there. It's too complicated for me to figure out all the detail. But what I can do is figure out which term is basically going to control what the top looks like, figure out which term is going to control what the bottom looks like, and that'll give me a pretty general picture. That's a lot easier to work with. So, which term in the top is going to control what the top looks like?
8x to the third.
8x to the third. So 8x to the third is the, what does that stand for again?
End behavior model.
Right, 8x to the third is the end behavior model for the top. What about the end behavior model for the bottom? Which term is going to control what the bottom looks like?
X to the 4th.
Yep, x to the 4th. So that's the end behavior model for the top. That's the end behavior model for the bottom. What do you think I would do with the two of them to get the end behavior model for the whole thing?
Average them?
Not average them, but think about how they were written originally.
Divide them?
Divide them. Yep. You divide them. So this function, which I'm calling f of x, is exactly what I wrote in blue. It's going to be approximately 8x cubed divided by x to the 4th. And look at how much simpler that is to work with than what you started with. Is it an exact copy of what it's going to look like? No. Is it a general idea? Yeah. And that's what we're going for, just kind of a general idea. So does everyone understand why it's approximately?
Yes, but so it's asking for the, like, what is it asking for? Like, in a problem, how would you know that you're supposed to find the EVM? It's just it would say, like, find the general EVM, or like, what's the...
So in the question, it would say, find an EBM. That's what it'll say.
Okay, fine.
Yep. We haven't got here yet, but it's going to say, find the EBM. And that's what I'm showing you right here. Now, this simplifies a little bit. This means 8 times, what does x cubed mean?
X to the 3rd power, so 8 times 8 times
Not 8 cubed, x
times
cubed.
X times X.
Yeah. So 8 times x times x times x. And what does x to the 4th mean?
X times X times X times X. But the X is above, so it's just 8x on the top. Or no, sorry. 8
Careful.
And then X on the bottom.
Yes.
Sorry.
Cancels, 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 but you are left with 1 in the bottom. And that is the EBM of that entire graph.
So you would keep simplifying it until you got it.
Something like that.
Okay.
Yep. So if I graph what's in this black box, and I graph that whole thing in blue, and I zoom out far enough, they're going to look exactly the same. That is a simpler version of that without all the details. Okay. Any question on that one? All right, so let's put an arrow over to that. That's the EBM for that original rational function I wrote in blue. Okay, we found the EBM of the top, found the EBM of the bottom, and then we divided the two. Now,
Do you find the EBM for anything else, or just rational functions for now?
generally just rational functions. Yeah, that's all we'll ever do, just rational functions.
It said something about asymptotes. Will we be having to worry about that, or just the EBM for now?
So that's what we did yesterday.
Oh.
So we're going to tie in what we did yesterday in the next problem.
All right.
Yep, it's going to be the same thing as yesterday. Okay, so first thing it says is to find the EBM. So let's start with that. What is the term in the top that's going to control everything that's happening? Yeah, this -1, that doesn't even really make a difference. It makes a very small difference. 2x squared. And what about the term that's going to control everything in the bottom?
3x squared.
3x to the third.
3x to the
yeah.
third. And that means 2 times what's x squared?
X times x.
Times x. And what's x cubed?
X times x times x.
So basically what happens here is there's a difference of 1 between the x's, and the bigger one was in the bottom. So that's where the x is left. It's in the bottom. So what would be the EBM?
2 over 3x.
Yep, 2 over 3x. Any question on the EBM? Now, if you can find the EBM, the horizontal asymptote is very easy. Okay, so in the EBM, let x get big. And simplify it. If you let x be a really big number and you simplify it, that's your horizontal asymptote. It's going to be a number. All right, so let's see if we can do it. When you write the equation of a horizontal asymptote, what letter is always by itself on the left? What letter? Y. There's going to be a number that goes here. The number that goes here, take the EBM and let x get really big. Like what's a really big number for x?
1,000.
1,000. Okay. What's 3 times 1,000?
3,000.
And if you take 2 and divide it by 3,000, you get a number that's pretty close to what? Pretty close to 0. Right? Take 2 and divide by 3,000.
6.66667.
That's scientific notation. It says 0.0006 repeating. 0.0006 repeating. Now, what's an even bigger number than 1,000?
A million.
A million. What's a million times 3?
3 million.
3 million. What's 2 divided by 3 million? It's
Very
even
small.
very small, even closer to what? 0. So that's how you find your horizontal asymptote.
So, like, for the most part, the horizontal asymptote is just going to be 0.
It's either going to be 0 if there's an x in the bottom, or it could be a number that's not 0, which I'll show you in a second. But anytime you're left with an x in the bottom and no x's in the top, yes, the horizontal asymptote will always be 0. So it's a lot easier to figure out the horizontal asymptote with that than go back and look at the original problem and try plugging a big number in for x there. That's a lot more complicated because you got cubes and squares and all these things. So that's what the EBM does. It gives you a simpler formula to work with to find the horizontal asymptote. Yeah. Oh, no question? Okay. All right, let's try this one. Let's start with the EBM. What's going to be the term that controls everything in the top? 2x to the fourth. And what's going to be the term that controls everything in the bottom?
3x to the 4th.
3x to the fourth. What happens this time with my x's?
They
They're all
completely
cancel
cancel
out.
out, so it's just 2 over 3.
I just get 2 over 3. So this is an EBM that doesn't have a letter in it. And that can happen, that's fine. So the EBM is 2/3.
So how would you find the y?
So now, now we're going to find the horizontal asymptote. To find the horizontal asymptote, it's still the same directions I wrote down. Look at the EBM and let x get really big. Okay, so look at your EBM. Here's your EBM right there. In that box, I want you to let the x get bigger and bigger and bigger, and tell me what happens to what's in that box.
What x?
There's none, so it's 0.
So there's no x in that box.
So
So what happens to the number in this box?
It's the same.
It stays the same.
No, so it's y equals 2 over 3.
So it's y equals 2 over 3. Okay, when all the letters cancel out and there are none left, letting x get bigger and bigger doesn't do anything because there's no x here. But those are the only 2 cases we're going to look at today. So the horizontal asymptote is either 0 or a number that's not 0. Any question on that? All right, so the last thing we're going to do is we're going to try to draw a sketch. Okay, if we get through the whole sketch today, that's fine. If we don't, there's nothing planned for tomorrow, so we'll just finish this up like we did the first thing today. So for today, we are always going to sketch problems like that. Are we going to do that next week? No. We're going to flip that around next week. Okay, but for this week, the exponent in the top will always be smaller than the one in the bottom, or equal to the one in the bottom. Look at this case. Was the exponent in the top smaller or equal to the one in the bottom?
Smaller.
Smaller. In this one was the biggest exponent. Yeah, it was equal to the biggest one in the bottom. Yep. So when we talk about the degree, we're talking about the biggest exponent. So the biggest exponent in the top will always be smaller than the one in the bottom or equal. So how do you sketch a graph of a rational function? Well, one thing that can be helpful is to figure out where it crosses the x and y axis. Is that always helpful? No. Because you could have a graph that does this. It never touches either axis. So sometimes it's helpful, sometimes it's not. Okay, it kind of depends.
I don't understand. I don't understand what you're doing here. I hear what you're saying. I just don't know.
So I'm going to show you about 4 different things that you need to draw a picture of a rational function. And these are all little things that are going to help you to draw the picture.
Okay.
So one thing that's helpful is if it crosses the x-axis, like you find this point and this point, and maybe your graph, does something like that. Okay. But finding those 2 points will be helpful. Okay. The next thing that we're going to need when we're sketching a rational function is you're going to need to find the vertical asymptote. The vertical asymptote, it's easy to remember how to find that. It's the numbers that would cause you to divide by 0. That's what we did yesterday. When you write a vertical asymptote, what letter is always by itself?
X.
Yep, x equals. So that's another, we'll call it like another thing that's going to help you to draw the picture. You need the vertical asymptote. The other thing you need is the EBM. That's what we learned today. And remember, the EBM is helpful for the horizontal asymptote. That's all we can do by hand. Okay, what we're going to need now is we're going to need the calculator. If I had something like this, can I plug in 2 for x?
No, because that'll make it 0.
I would make it 0 in the bottom. Could I plug in something close to 2?
Yeah.
Like 1.999?
So we found the vertical asymptote.
Yeah, so let's say we found a vertical asymptote, it's at 2. I can't plug in 2. But could I plug in 1.9?
Yes.
Yeah, could I do like 2.001?
Yes, sir.
Yeah, that's fine. So what we're going to do is use the calculator to not plug in a number that's the asymptote, because that's going to give us an error. We're going to plug in a number near the asymptote. And what that's going to do is it's going to give me a point on the graph that I can draw my line through. Or in this case, it's going to curve.
So we would. I think. Go.
Okay, so we're going to use the calculator to get a point near the asymptote. And then we can always check our answer on the calculator to make sure we did it right. So those steps describe the rest of the problems we're going to do. I had 3. We're not going to get to 3. We'll try to get to 1. We'll do 1 today, and then we'll try the other 2 tomorrow after we do the homework. And then you'll have the rest of the time to do the study guide for the test. Okay, does everybody have the five steps?
1 second. I don't know.
Yeah.
Okay, yeah, just sign out, and there'll be a video online later today. Okay, so we are going to sketch a graph of that, x minus 1 divided by x squared minus x minus 6. First thing, when you have a quadratic, there was one in the homework last night where you had to use quadratic formula. You will not have to use quadratic formula for any of this. Okay, doing a sketch is already hard enough, so complicating it with quadratic formula, I'm not going to do that. So if you're not going to use quadratic formula, that means the bottom is factorable. Can anyone tell me how you would rewrite the bottom factored?
X minus 2, x minus 3.
Well, we got to have 1 minus and 1 plus.
So x minus 2, x plus 3.
X minus
3. X plus 2.
x plus 2. That's x squared plus 2, take away 3 is negative 1. And if you're wondering why did we factor that, we need to know the 2 numbers that make the bottom 0. Now we can figure that out. Okay, let's look at our steps. Oh, they're on the same page as the problem. That's fine. Okay, step 1, find the vertical asymptotes. Where are the numbers that would make the denominator 0? Okay, how many numbers make the denominator 0? 2. Vertical asymptotes always start out with what letter? X. What are the 2 numbers that would make the denominator?
3 and negative 2.
3 and negative 2. Okay, let's sketch those. So we're going to have vertical asymptotes at 3, and we're going to have a vertical asymptote at negative 2. The way we generally sketch a vertical asymptote, just put it as a dotted line. 3 and negative 2. Any question how I got those 2 dotted lines?
Like how you physically.
Yeah, just why I put them where I put them. Okay. Step 2. Okay, so we did the asymptotes. I'm not worried about the intercepts right now. Let's find the EBM. What's the term that's going to control what's happening in the top? X. And what's the term that's going to control what's happening in the bottom?
X squared.
X squared. And that simplifies to 1 over x. Okay, so there's my EBM. Now, let x get really big. And tell me what would happen to what's inside this box. Can we get close to 0? Yep, get very close to 0. Okay, so that's my horizontal asymptote. That's a horizontal line at what number?
0.
At 0, yep. So these grid lines that I set up for asymptotes, they basically give me boundaries where my graph is going to be, and it can't cross these dotted lines.
So it'll go to 0 because if x equaled 100, 1 divided by 100.
It's close to 0. Yep. And the bigger you make x, the closer it gets to 0. All right. Let's see if we can find the y-intercept. That's an easy one. We'll just plug in 0 for x and see what we get. If you plug in 0 in the top, what do you get? So we get -1. And if you plug 0 in the bottom, you get 0, -0, -6. So where does it cross the y-axis? Well, negatives cancel. 1/6. So, okay. So that's my y-intercept.
How do you find those numbers? -1, -6.
So to find the y-intercept, plug in 0 for x. That's how you find your y, because your y-intercept is always 0, comma, and then a number. All right, now we need the calculator to do the last step, which is to check some points near each asymptote. I just type the original one in. You don't need to type the one you factored in, especially if you made a mistake. Just type in the original. So we've got x minus 1 divided by x squared minus x minus 6. Okay, I don't even need to hit graph. I just want to go to my table. What were the two numbers that I can't plug in? So don't plug in 3 and don't plug in -2. You're just going to get an error. Let's plug in a number a little bit smaller than -2. -1 is bigger. I want to go to the left. But I want to be very close.
-2.1.
-2 point, let's go even closer. -2.001. I'm at -600. So when I go to -2, where's -600?
Way down.
Way down. It's way, way down. Let's plug in a number a little bigger than -2. 1 point what? Yeah. When I go just to the right, -1.999, I'm way up at 600. Okay, let's check 3. What's a number that's just a little bit smaller than 3?
2.99.
Yeah, I'd go really close. 2.999. I'm at -400, which would be where?
Yeah.
Way down here somewhere. It's way, way down. And how about a number just a little bit bigger than 3? 0.001. And we're up at 4,000. So it's up very, very high.
So what is finding this to?
So we're getting some points so we can make our sketch. Okay, let's pick 2 more that are on my grid. I got 10 and -10, just because that's the edge of my graph. At 10, I'm at 0.1. So just barely above that line. And -10, that's the left edge of my paper. -0.1. Okay. So what's going to happen is this graph has to go through this dot, and it's going to try and head to the right, but can it cross that asymptote?
No.
No. So when it starts to get close to it, it's going to curve down and go through there. Same thing here. It's going to stay very close to that point, but can it keep heading down and go through that horizontal asymptote?
No.
No. The asymptote causes it to curve, like that. And the section in the middle, it has to stay very close to that asymptote, but it has to go through that dot. So it has to curve, but can it keep heading to the right forever?
No.
No, it gets stuck again by that other asymptote. And that's what the graph ends up looking like. If I do zoom 6, let's see how it looks. How does my graph compare to the one on the screen?
Yep.
It's close. Yeah, it should be a little flatter in the middle, but that's okay. I got the general idea. So we'll practice more of that tomorrow. And for tonight, let me just change a couple questions. It's not a ton of questions anyway, but I'm just going to take a couple off. And we'll do them in class. Okay, so 29 is okay, 32 is okay. Okay, don't have to do 24. And you don't have to do 18. So we'll do 17 and then 19 to 22. Okay, and I think everything else is okay. Yep, so we'll look at that tomorrow.